Hello and welcome to lecture 37 of analog integrated circuit design. We were discussing the two-stage op amp. We have calculated the small signal parameters offset and noise. We also saw that offset is contributed by mismatch between transistors in the first stage as well as the biasing condition of the second stage. If we make the current density in the second stage transistor equal to the current density in the load transistors of the first stage, the systematic offset can be avoided. Now, we will calculate the slew rate and signal ranges, that is input common mode range and output signal swing of the two stage op amp. This is the two stage op amp, plus input, minus input and the output, and this is the integrating capacitor C. Now, we have to assume that there is some load here and the load will be connected between the output and ground if it is a capacitive load. If it is a resistive load, we will see later what to do with it. I will assume that there is only a capacitive load for now. Okay. And let us say the tail current of the input stage is I naught. The slew rate as usual is limited by the amount of current flowing into some capacitor, which limits the rate of change of voltages inside the op amp. Okay. As before, if we test the op amp in unity gain configuration, that is, I make this circuit and apply a step and look at the maximum rate of change of the output voltage. The input is V by S plus some step V I. Now, we know that for larger and larger values of V I, the incremental current in M2 becomes larger and larger. For very small values of V I, the total current here will be I naught by 2 plus GM1 times V I. As V I increases, the current in M2 becomes larger and larger, but the increment cannot go beyond I naught by 2, that is, the total current in M2 can only be I naught. At that point, 0 current will be flowing through M1, and all of that I naught will flow from the integrating capacitor C. Okay. That will be equal to I naught for large values of positive V I. Okay. Now, similarly, for large values of negative V I that is large and negative, all of the current will flow through M1 and nothing will flow through M2, and there is a current I naught that can go in that direction. Okay. So, what is the rate of change of the output voltage? First of all, rate of change of the voltage across C, okay, this voltage V C, that is equal to plus minus I naught by C, okay, assuming that a current I naught will flow through the capacitor. Now, what will be the output voltage? Remember, if you recall the representation of the two stage op amp at the level of transconductors. This is what we have, okay. GM2, GM1, C and CL. Now, the second stage is supposed to be a current controlled voltage source, and it becomes a current controlled voltage source because the voltage at the negative input of GM2 is very small, okay. If GM2 becomes very large, if the second stage has an ideal op amp, this voltage will be at 0, okay. So, this voltage is approximately 0. So, Vc is simply the output voltage itself, Vc equals V naught, okay. So, this is not only the slew rate of the voltage across the capacitor, but it is also the slew rate of the output, okay. So, it looks like the slew rate is similar to what we would get in a single stage op amp, but we have to consider other things here. Let us say that V naught, which is Vc, is changing at some rate, okay. V naught is changing at a rate of I naught by C. Now, what does it mean? The voltage across CL, which is V naught, is also changing at this rate. So, the current through CL is the slope of this voltage times the capacitance, okay. So, the current through CL would be CL times I naught by C. Similarly, if the output voltage was reducing, if the output voltage was doing something like that with a slope of minus I naught by C, there would be a current in the other direction, okay, but also of value CL times I naught divided by C, okay. Now, let us examine these two cases separately. First, let me take the first case where a current I naught is drawn this way. So, that means that the output is ramping up at plus I naught by C, and that means that a current of I naught times CL by C is flowing through the load capacitor, okay. Now, what does it mean? Through M11 we need to have a current equal to the current in M12, which is some bias current I12 plus the current through C plus the current through CL, okay. So, this is I12 plus I naught times 1 plus CL by C, okay. ID11 will be I12 plus I naught 1 plus CL by C. Now, is it possible to have that value? Yeah, because in quiescent condition the voltage here would be such that the current through M1 equals I12, okay. Now, as Vi increases, this voltage reduces slightly and that increases the current in this, okay. Now, the total current here is limited by how far the voltage can go, but we will assume that it is not limited. So, the current in M11 can increase in the positive direction, okay. So, in this direction current in M11 can increase, while it is I12 it can easily become this value by lowering of the gate voltage, okay. Now, this may be a little confusing. Earlier while calculating the output voltage, I assumed that the voltage at the gate of M11 is hardly changing. So, this is just an approximate calculation, okay. For current in M11 to increase, the voltage here has to decrease. So, but we just to be able to calculate the output voltage, we assume that this is fixed for calculating the output voltage, okay. Now, by lowering the gate voltage of M11, the current in M11 will increase, okay. So, it is indeed possible to have this current in M11. Now, let us see what happens in the other direction. Let us say that is I naught and that is I naught CL by C, okay. And this is some I12. So, the current through M11 will be I12 minus I0 times 1 plus CL by C. Now, is it possible for this to attain any value? Clearly not. In the quiescent condition, I12 is flowing through M11, and when we reduce Vi, I0 flows this way, I0 flows that way, and the output voltage will reduce. Okay. Then the current in M1 will reduce. Now, the smallest that the current in M11 can be is 0. Okay. The current in M11 will reduce, and the smallest value of the current in M11 is 0. So, what does it mean? ID11, which is I12 minus I0 1 plus CL by C, must be greater than 0. Okay. Now, if this is the case, if I12 is greater than I0 times 1 plus CL by C, the output will reduce at a rate of I0 by C. Okay. But what happens if I12 is less than I0 times 1 plus CL by C? What happens in that case is that as we apply a negative step to Vi and make the size of step larger and larger, more and more current will flow into the integrating capacitor. Okay. Now, before all of a current I0 can flow through this, the transistor M11 will cut off, okay, because I12 minus the current in this minus the current in CL will become 0. Okay. The current in CL will always be the current in C times CL divided by C, because the output is changing at the same rate. Okay. The voltages across the two capacitors are changing at the same rate. So, M11 will cut off before the input differential pair can switch completely. So, in that case, the output slew rate will be I12 divided by CL plus C. Okay. This is because the total current in C and CL must be equal to I12 when M11 cuts off. When this cuts off, some current is flowing there and some current is flowing there, okay, and the sum of the two equals I12. If that happens, then the rate of change of the output will be I12 divided by CL plus C. Okay. So, in the two stage op amp, the positive slew rate is I0 by C and the negative slew rate is whichever is smaller of I0 by C and I12 by CL plus C. Okay. So, there are two mechanisms of slewing. Either the input differential pair can cut off, in which case maximum current out of the first stage will be equal to I0. Alternatively, the second stage can cut off, in which case the maximum current through C plus CL would be I12. Okay. Now, which of these is limiting depends on the value of I12 and I0. Okay. So, it is possible for the negative slew rate to be either I0 by C or I12 divided by CL plus C. So, this comes out of some simple calculation. This is actually an approximate calculation, because we assume that at the input of the second stage we have 0 volts, but this is good enough for practical purposes. So, this also means that if the current in the second stage is very small, then we will end up with a rather small slew rate, okay, in one direction, and it is also possible for the slew rate to be different in the positive and negative directions. Okay. Now, the next thing is the signal swings. The last thing we have to determine here is the signal swing. Okay. Signal swing limits. Let me remove this feedback loop. Now, what are the limits on the input bias voltage V bias? We have evaluated this many times. If the input voltage V bias increases, the input transistors M1 and M2 can go into triode region, and if the input V bias reduces, the tail current transistor M0 can go into the triode region. Okay. So, the limits are exactly the same as before. The maximum value would be the drain voltage of M1 plus 1 threshold voltage. And the minimum value would be the overdrive voltage that is required across M0 to keep it in saturation region plus the VGS of M1, that will be VT1 plus VD sat 1 plus VD sat 0. Okay. You can see that it goes very close to VDD, but somewhat far away from the ground. Okay. And what is the limit on the output? As V0 increases, there comes a point where the voltage across M11 is too small for it to remain in saturation region. So, V0 has to be less than VDD minus VD sat 11. Similarly, as V0 decreases, the voltage across M12 becomes smaller and smaller, and at some point it will go into triode region, okay, and that will be VD sat 12. Okay. So, you can see that this kind of output structure, where we have a single transistor connecting to the supply voltage and a single transistor connecting to ground, will give the maximum possible swing limit. It can go within a VD sat of the upper rail and within a VD sat of the lower rail, which is ground. Okay. Now, in general, this is the maximum swing that is possible in an integrated circuit. This is the maximum possible swing in a transistor circuit. Okay. Now, there are some special circuits where the voltage can go above the supply rail or below the lower supply rail. We will not consider that. In general, you have to leave at least one VD sat room on top and bottom. Okay. So, to summarize, the two stage op amp has a DC gain, which is the product of the first stage and the second stage gain. And the important thing is that even if you have a resistive load GL with a very high conductance, it affects only the second part of this term, and the first one can remain very large. Okay. So, that is how we will be able to operate the op amp with resistive loads. And the frequency response can be written as GM1, the transconductance of the first stage, and a 0 on pole which appear due to current mirroring, and the right half plane 0 . This should be the DC gain A naught, the right half plane 0, and the dominant pole and the non-dominant pole. Okay. Now, these we have spent a lot of time evaluating. I am not going to write down the expression. The dominant pole appears at the output of the first stage and the non-dominant pole at the output of the second stage. Okay. And the noise and offset are contributed mainly by the first stage. So, the input referred noise voltage spectral density is that, and the input referred offset voltage is that one, and we also calculated the slew rate and the swing limits. Okay. So, what does the two stage op amp offer us that the other op amps that we studied so far do not? First of all, it has a higher DC gain, it is of the order of GM by GDS square if it is a capacitive load, and even with a resistive load, the first stage can be designed to have a substantial amount of gain. Okay. The noise and offset are contributed only by the first stage. So, it is similar to what we would get in a differential pair. Okay. And the slew rate depends on whether the first stage or the second stage is limiting it. It can be similar to what we get in a single differential pair stage. And finally, the signal ranges, the range of the input bias voltage and the output voltage are the largest we have seen so far. Okay. The input bias range is the same as what we would get in a simple differential pair stage, and the range of the output voltage is the largest that is possible, that is within a VD sat of the upper rail and a VD sat of the lower rail. Okay. Before we go further, a quick clarification on how we connect the load to the two stage op amp. As I mentioned earlier, we are operating with single supplies. So, the input signal and the load must be connected to some bias voltages. We have VDD on top and the ground on the bottom. So, the input will be some V bias plus Vi. I have taken a voltage follower as an example, but it can be any circuit. Okay. And the load that we have must also be connected to V bias. Okay. So, what happens is if Vi is 0, the input is at V bias, the output is at V bias due to feedback. So, no current will flow through RL. Okay. In fact, this is a very similar situation to having the conventional picture of the op amp with a dual supply and the load going to ground. Okay. As was explained earlier, simply by shifting all the voltages in this circuit, we get that circuit. Okay. Now, if we have only a capacitive load, it is not necessary to connect it to V bias, we can connect it to any voltage. Okay. Because even if you have some DC across the capacitor, it is not going to draw any current. So, if you have only a capacitive load, it can be connected to any voltage. Okay. So, this V term can be anything, but if you do have a resistive load, if the voltage on the right side is anything other than V bias, even in quiescent condition, some current will be flowing out of the op amp. Okay. What this means is, let us say I have a resistor here RL, and this is at some V bias that is different from the quiescent output voltage, then a current will be flowing through that has to be supplied by the transistor M11. Okay. So, that is not a good way to operate. It is best to connect the resistive load such that the quiescent output current is 0. Okay. So, when we do have a resistive load, we connect it up to V bias. Okay. Now, what else is there with these op amps? We have discussed the single stage op amp and the two stage op amp. We can make a 3-stage op amp by just following this procedure. Okay. I will not discuss that in great detail, but I will just put down the topology here. We know that at the signal level, what we need are three stages. So, this is the input of the op amp and that is the output. We can think of it as the input GM1 driving a current controlled voltage source with a trans admittance SC or a trans impedance 1 over SC, and the current controlled voltage source is made using this 2-stage op amp. Okay. And the 2-stage op amp itself can be thought of as GM2 driving the current controlled voltage source with a trans admittance of SC2, okay, or trans impedance of 1 over SC2. Now, how would we go about implementing this? It is a simple extension of the 2-stage op amp that we have. Let us say we continue with the same topology. Now, this forms the second stage GM2. Okay. So, this is GM1 and it is required to take the difference between two inputs and provide an output current, and GM2 is single ended in that one of its inputs is at ground, and GM3 now we have the freedom to choose either an NMOS stage or a PMOS stage. Just for variety, let me make this an NMOS amplifier. Okay, where this PMOS is biased at some fixed voltage. Okay. Now, as usual, that is derived from some current mirror. Okay. So, this is GM3. Now, we have to connect the integrating capacitors, that will be C2 and this will be C1. Okay. Now, here I am not showing refinements like possibly connecting resistors in series with C and so on. Okay. So, this is the output. This is the negative input, that is the positive input of the op amp. Okay. Now, exactly as we did before, you can analyze this. In fact, the transfer function has already been analyzed and you can do the exact analysis including the zeros and so on. The principle is the same, the non-dominant poles and zeros must be sufficiently outside the unity loop gain frequency, so that the system is stable and well behaved. Okay. Now, at the transistor level, the more stages you go to, the more degrees of freedom you have. One obvious one is now whether to choose an NMOS transconductor or a PMOS transconductor in the third stage. I have drawn it with an NMOS transconductor, but the other way around is equally possible. Okay. Now, you can also analyze all the other parameters like the noise, offset, slew rate, swing limits and so on. In fact, it is very obvious that the swing limits will be similar to that of the 2-stage op amp. The input bias voltage limits are the same and the output voltage can be within 1 VD sat of the supplies. Okay. The slew rate can also be calculated it is also limited by the current in the first stage going into some capacitor, and there is a possibility of the current in second or third stages limiting the total slew rate. Okay. As far as noise and offset are concerned, as with any multi-stage amplifier, they are dominated by the contribution from the first stage, and the expressions will remain exactly same as that for the two stage op amp or the simple differential pair single stage op amp. Okay. Now, one thing I did not mention earlier, let us say we have a two stage op amp. One of the refinements we can do to this to make it more stable is to add a resistance in series, okay, so that the right half plane 0 is cancelled. It is implemented exactly as we did in the signal level, that is at the level of the transconductors. The value of RC has to be equal to 1 over GM11 in this case, 1 over GM of the transistor M11. Okay. So, now to ensure that may be difficult if you use a real resistor. So, the resistor that you put there has to be matched to the reciprocal of the GM of the transistor M11, and sometimes what you can do is to implement the resistor also as a MOS transistor in triode region. So, that the matching across process and temperature corners is good. Similarly, if we want to tailor the zeros in series with C1 or C2 or both, we can connect resistors in a 3 stage op amp. Okay. This is a 3 stage nested Miller compensated op amp. Okay. Let me copy over this circuit just to illustrate a couple of more details. So, first of all, as I have been mentioning several times, the gates of M0 and M22, M12 and so on are not connected to fixed voltages, they are always derived from current mirrors. Okay. Let me call this M0 prime and this is I0 prime. Okay. As usual, whenever you make a current mirror, you make the lengths of all transistors the same and the widths are in the ratio of the currents that you want. So, let us say this is I0 and this is I12. That means that I0 by W0 should be I12 by W12, which should be I0 prime by W0 prime, and L0 prime and L0 and L12 should all be equal to each other. Now, let us say that we did not want to make the length of M0 and M12 equal to each other, then the best thing to do is to not use common biasing line for M0 and M12, but bias this separately from another diode connected transistor. Okay. Similarly, VG22 has to come from some diode connected transistor, okay, which also is the same in length, and the width ratio is such that the current ratio is as required. Okay. So, that is how we bias the op amp, but it is very cumbersome if we show every transistor in the circuit. So, it is very frequently not shown, these current mirror devices are not shown and we show only that much. Okay. Now, the other thing is we have a current source going into the drain of the transistor and there is no other path for the direct current, the DC. Okay. Similarly, M22 is a current source that is feeding into the drain of M21. Now, how is this biased properly? Because normally if I have something like this, so let us say Ix and this is a MOS transistor, then what is going to happen? How much will be the current through this transistor? unless there is feedback around this transistor, we cannot say that the current in this will be equal to I x. Okay. The transistor is a unilateral device, it is only by adjusting the VGS that we can change the drain current. We cannot apply a current to the drain directly and expect the VGS to be established automatically. We have to provide a feedback from the output, from the drain side to the input side to VGS, so that the correct VGS is established for whatever bias current we want to have. Okay. Now, in the op amp, the way we have drawn it, the current sources are going directly into the drain and nowhere else. Obviously, as you know, the op amp can be used only inside a feedback loop. Okay. Let me again for illustration consider a unity gain follower. Okay. What happens in that case? I will have a connection from there to there, and the plus input, let us say, is biased at some V bias. Okay. Now, if you think of, let us say, this M11 M12 stage, let me redraw that here. So, this M12 is a current source. So, I will show it as a current source. This is I12. Okay. There is feedback through this M21 and through the input differential pair. Okay. Now, if you see from here to there, there is an inversion. This is a common source amplifier, and from there to the drain of M2, there is an inversion. So, what we have is some amplifier with a positive incremental gain feeding back to the gate of M11, and we know that this is exactly what we need. Okay. If the voltage here increases, that means that the current in M11 is too much and the gate voltage should be increased, so that it reduces, okay, and vice versa for smaller currents. Similarly, if you think of M22 and M21, M22 is a current source I22, and this is M21. Okay. So, that again the gain from here to there is negative and gain from there to there is negative, it is a common source amplifier. So, we have a positive incremental gain amplifier connecting that way, and we know that if we do that, M21 is in a negative feedback and a current of I22 flows through that. Okay. So, if there is DC negative feedback around the entire op amp, each of these stages will be in feedback and everything will be biased correctly. Okay. If you operate the op amp in open loop, there is no guarantee that the bias currents will flow through the transistors, okay, because we have to establish the VGSs for these transistors for the correct current to flow. Now, while discussing op amps, you would already have heard that you have to use them in negative feedback, and this is the reason. Okay. If they are not in negative feedback and you apply a 0 differential input voltage, there is no guarantee that the op amp will be biased properly. Okay. In fact, because of mismatches and so on, there is almost a guarantee that the transistors will all be in some triode region. Okay. One of the transistors will always be in triode region. So, that is about DC negative feedback around the op amp. Now, let us say the two stage op amp gives you a gain of the order of GM by GDS squared. Let us say we want an even higher gain. What should we do? We can go for a 3 stage op amp, and we can go for a 4 stage op amp and so on. That is possible. That is one of the ways of doing it. Also, there are other ways. If all we want to do is to improve the DC gain, what did we have? We have a single stage op amp of some GM1, and this is just the differential pair. It has some GO1 and the DC gain is of the order of GM by GDS of a single transistor. You can also refine this by going to telescopic or folded cascode. Okay. What that will do is to have a similar topology, but the gain will be of the order of Gm by Gds squared. Now, when we had a 2-stage op amp, we used a simple differential pair here, okay, followed by a second stage, that is M11 with a current I12. What we can instead do is to use the telescopic or the folded cascode in that stage. Okay. If we do that, what happens is the gain of the first stage increases, it will be of the order of Gm by Gds squared, and the second stage will have a gain of Gm11 by Gds11 plus Gds12 plus Gl. Okay. So, by increasing the first stage gain, we can increase the gain of the overall op amp. So, we can still stay with 2 stages, which means that the compensation scheme, the scheme to make the op amp behave like an integrator is the same as in a 2-stage op amp. Okay. But the difference is, so we can stay with just 2 stages and have a higher gain by making the first stage a telescopic cascode op amp or a folded cascode op amp. Okay. So, this is a very commonly used technique, as what has happened is that as you go to finer and finer technologies, that is with shorter and shorter channel lengths, the problem is that the Gm by Gds of transistors is becoming smaller and smaller. Okay. This is simply because the length is becoming smaller. Now, you can make the length higher and get a higher value of Gm by Gds, but that reduces the speed. So, if you stay with a shorter channel length, the way to increase the gain is to go for a cascode first stage and a second stage. So, that with 2 stages you get a very high gain. Okay. So, that is very much possible, and that is also quite frequently done. Now, another possibility is that we use not just one cascode, but 2 cascodes. Okay. Usually such a thing is called a triple cascode. I will show it for the telescopic cascode topology. Now, just to illustrate the principle, I will show also just a common source amplifier. Looking in here, let us say this is M1, I will have GDS1 as the output conductance or RDS1 as the output resistance. If I cascode it with MC, the output resistance will be GMC by GDSC times RDS1. I could cascode it with one more transistor, let us say MC prime, the output resistance will be GMC prime by GDSC prime, GMC by GDSC times RDS1. Okay. So, it is even higher. So, the same thing can be done with the op amp as well. So, this is a diff pair with 2 cascodes. Okay. We had M1, M2, M5, M6 earlier, and let us say I call it M5 prime, M6 prime, and similarly on top I need to have a current source with 2 cascodes. Okay. There is no point improving only one side when both sides are contributing to the output conductance. So, I should have a current mirror which is also triple cascoded. So, you need to establish the bias voltages at all these points, so that all transistors remain in saturation, and of course, a similar thing can be done with the folded cascode as well. Also, an additional constraint is that you have now stacked more transistors. So, that means that things will be constrained even more than before. Okay. So, you can have more and more cascodes, but you will have lesser and lesser swings, but when you have a two stage op amp, the swing at the output of the first stage does not have to be very high. So, it is possible to do this. Okay. So, sometimes when you want even higher DC gain, you could go for something known as a triple cascode in the first stage and a second stage. Okay. So, there are lots of alternatives and lots of possibilities. This is one of the reasons why you should not try to remember topologies, okay, without understanding what is going on behind them, because I have some basic topologies, I can combine a number of them in very different ways to get seemingly very different alternatives, but once you understand the underlying principles, they are all the same. Okay. So, we started with a single stage differential pair op amp, we went to telescopic and folded cascodes, that is one way of increasing DC gain. We can go to two stage op amp, that is another way of increasing the gain. So, in some ways the two stage op amp and the telescopic or folded cascode will have the same DC gain if you have only a capacitive load. If you have a resistive load, you can't use only a cascode stage, okay, because that only increases the output resistance, that does not increase the transconductance. Now, if you want a further increase in gain, you can go for 3 stage or 4 stages, or you can go for a triple cascode telescopic stage or a triple cascode folded cascode stage. Alternatively, you can combine the two, you can have a telescopic cascode stage followed by a second stage, or a folded cascode stage followed by a second stage, and so on. Okay. The possibilities are endless, and it is up to you as a designer to pick which is the right one for you. If you understand the trade offs very well, you will be able to do that. Okay. Now, as usual in design, you have a number of parameters, and you will not be able to put down all the parameters on paper and then churn some equations and get the dimensions of all transistors. Okay. So, it is very important to understand what to change if something is deficient. Okay. Let us say you design a two stage op amp and you find the DC gain to be too little. What can you do? You have to increase the gain of the first stage, that is an easy possibility. So, you increase the length of transistors in the first stage, or you go for a cascode first stage. So, those are all the possibilities. Okay. Similarly, let us say you find that the input referred noise of your two stage op amp is too much, then what will you do? You know that the noise is being contributed only by the first stage. So, you have to manipulate the first stage in some way, and you would not like to affect the transfer function at all. Okay. So, you do noise scaling for the first one, you do impedance scaling or noise scaling for the first stage. Now, that will increase the transconductance of the first stage. So, that means that you also have to change the integrating capacitor, so that your op amp behaves in exactly the same way as before. Okay. So, you may have to change different things by keeping some other things constant. So, if you understand the basic principles very well, you will be able to do this quite easily. Okay. This is a quick summary of the op amps as we have studied them so far. This is the differential pair op amp. Now, the output resistance can be calculated using this. We know that the output resistance of the cascode is given by this formula when we have a resistor with conductance Gs in the source of the transistor MC. So, if we have another transistor, it will be GDS 1 instead of GS. Okay. And finally, if we have a differential pair, it is as though this transistor M1, the impedance looking at the source is at the source of this transistor MC. Okay. So, the R out is 1 over GDSC times 1 plus GMC by GM1. Okay. And if GMC happens to be equal to GM1, this is simply 2 by GDSC, or the output resistance is 2 times RDSC. Okay. And the following slides show all the op amps with bias values in black, the incremental values in red, and the impedances in blue. The total quantity of course is bias plus increment. So, we said that this and that voltage are equal by symmetry, that is how we started the analysis. So, if we terminate this with VDD minus VGS3, nothing will flow there, and I naught by 2 will flow through all these 4 transistors, where I naught is the tail current. And to calculate the transconductance, we have these incremental voltages VD by 2 that causes a current GM VD by 2 here and GM VD by 2 in the opposite direction. So, a net current of GMVD will flow to the output. To calculate the output conductance, this is what happens. If we apply a test voltage Vt, we will have Vt times GDS1 by 2 flowing this way, and that will also get mirrored. So, Vt times GDS1 by 2 will flow there, plus Vt times GDS3. Okay. So, that is how we get the output conductance to be GDS1 plus GDS3. So, similarly, we can calculate the noise and the other parameters. We will continue with that in the next lecture. Okay.